So, next property has similarities to what is happening in the continuous time case. There if you convolved two functions x1 of t and x2 of t, the corresponding transforms got multiplied. Exactly the same property holds here. Therefore, x1 of n convolved with x2 of n has z transform x1 of z times x2 of z with ROC at least as large as the intersection of ROC1 and ROC2. Again, as in the linearity case, the ROC can be larger if there are pole zero cancellations. The proof is extremely simple. So, you have y of n. So, this is k going from minus infinity x1 of k times x2 of n minus k. So, this is the definition of the convolution. Therefore, y of z is sum over all n y of n z to the minus n, and this is wherever y is there, replace y of n by this expression. Therefore, this is k going from minus infinity to plus infinity x1 of k x2 of n minus k z to the minus n. And now again we will instinctively interchange these two summations, and to satisfy the mathematicians in us, we will put a question mark because this is true only under certain conditions. Therefore, this becomes k going from minus infinity to plus infinity. This is actually x2 of n minus k. Therefore, this is x1 of k n going from minus infinity to plus infinity x2 of n minus k times z to the minus n. This sum up over all n x2 of n minus k times z to the minus n is the z transform of x2 of n minus k. Therefore, we will use the delay property. Therefore, this becomes k from minus infinity to plus infinity x1 of k. This is nothing but x2 of z times z to the minus k, and this is nothing but x2 of z k going from minus infinity to plus infinity x1 of k z to the minus k, which by definition is x1 of z. Therefore, this is indeed x1 of z times x2 of z. And as a simple illustration of this, if you had x1 as a to the n u of n and x2 of n to be b to the n u of n, then x1 convolved with x2 of n would have transform 1 by 1 minus a z inverse times 1 by 1 minus b z inverse, and the ROC will be mod z very good. So, this will be greater than max of mod a and mod b. The corresponding dTFT is nothing but x1 of e to the j omega times x2 of e to the j omega. This is one of the most important properties because this is the property that gives rise to the concept of filtering. So, the concept of frequency domain filtering is based on this. So, suppose I have a system with input x of n, its impulse response is h of n, and then I have y of n, which is nothing but x of n convolved with h of n, assuming the system is LTI. Therefore, y of e to the j omega is x of e to the j omega times h of e to the j omega. Now, let us assume that h of e to the j omega is 1 for mod omega less than omega c and 0 otherwise. Therefore, frequency response h of omega is like this. So, this after all is the dTft, therefore, this is between minus pi and pi. So, this means that y of e to the j omega is guaranteed to be 0 for mod omega greater than omega c. So, any frequency component of the input that is outside minus omega c to plus omega c gets filtered out. So, this is no different from what was happening in the continuous time case, where you had looked at things like ideal low pass filter, high pass, band pass and band stop. Now, let us revisit high pass and low pass just to reinforce some of the similarities and also see some of the differences. So, this is your low pass filter. Now, in continuous time case, this is your low pass filter. The crucial difference of course is this. If you draw this from minus infinity to plus infinity, this figure will not change. From omega c to plus infinity, all frequencies will have 0 weight. Similarly, from minus omega c to minus infinity, all frequencies will get completely cut out. Whereas here, remember, the highest frequency in continuous time is plus infinity, whereas the highest frequency in the discrete time case is pi. Therefore, when you talk about filtering all frequencies above omega c, you are really talking about frequencies in the range omega c to pi. And if you drew this picture beyond minus pi to pi, for example, if you extended this, then you will see at omega equal to 2 pi, exactly the same picture will get repeated. What happened at 0 will also happen at 2 pi. What happened at 0 will also happen at minus 2 pi and so on. So, if you extend this picture beyond the range that is plotted, which is minus pi to pi, you will see periodic repetitions in the dTft case, whereas in the continuous time case, this is it. So, this is your ideal low pass filter. If you now talk about the corresponding high pass case, if the cutoff frequency is omega c, it will pass all frequencies above omega c. That is what the ideal high pass filter will do. From 0 to omega c, it will cut things out. So, this is what is going to happen. So, this is omega c minus omega c, this is h of e to the j omega, and the corresponding high pass in continuous time is this. The big difference of course is from omega c, it will pass all frequencies beyond omega c, therefore, this will go like this. On the other hand, in the discrete time case, this will also go from omega c to the highest frequency, only that now the highest frequency is pi. Now, if you complete the picture, this is how the response will look. All right. So, this is the response for the ideal high pass filter in the discrete time case, because if you periodically repeat this, what happened at 0 will also happen at 2 pi and also happen at minus 2 pi and so on. So, if you drew this with periodicity 2 pi, you will find that this is really part of the next repetition. Similarly, this is part of the repetition that is happening here, because what happened at 0 will also happen at minus 2 pi, and it is centered around minus 2 pi. If you drew this, you will see that these are the responses corresponding to the frequency response that occurs at minus 2 pi. Similarly, this is the arm of the response that happens at omega equal to 2 pi. Therefore, so this is the highest frequency in the discrete time case, whereas in continuous time case omega equal to infinity will be the highest frequency, alright. So, notice carefully the differences between these two cases. This is continuous time, this is discrete time. Continuous time things go from minus infinity to plus infinity. Discrete time case you are always limited to the range between 0 to 2 pi or between minus pi to pi, and in continuous time case the highest frequency is infinity. Discrete time case the highest frequency is pi. So, this is one of the most important properties, because in practice convolution and correlation happen all the time. Convolution is used for filtering. Your cell phone does filtering all the time. Your front end signal, it has to filter it to eliminate out of band noise and to concentrate only on frequency of interest. In this context, we talk about omega going from minus infinity to plus infinity here, and then we had also talked about Z. Actually, somebody made this remark in response to one of my questions. I did not respond to and elaborate on that answer then. Somebody said minus infinity when it came to Z, right. What about infinity in the variable is Z, for example? Because somebody did say Z going from minus infinity to plus infinity and so on. Yeah, Z is complex, therefore okay, so mod Z being infinity, all right. So, if mod Z, you can think of this as a circle mod Z equal to R and then let R going to infinity, right. So, does it mean then there are infinite number of points? When you are talking about real numbers, you have x equal to plus infinity and x equal to minus infinity, right. What about mod Z then? Are there infinite number of infinities there? Yeah, so that's precisely the question. So, does it mean there are infinite number of infinities? Because if you are on a circle and if you let the angle vary continuously, there are uncountably infinite number of points, correct? So, have you thought about what it means infinity when the variable is complex? So, you need to look up this Riemann sphere, all right. Look up Riemann sphere, and what it does is it is a mapping in which points in the 2D plane will be mapped onto the points on a sphere, and you will find that all points at infinity will get mapped to what is called the north pole of the sphere. So, in this mapping it is one to one and invertible. Therefore, when the variable is complex, infinity is really only one point, and that in the Riemann sphere mapping it maps to the north pole. So, you need to be clear that when we talk about complex variables, when we say z equal to infinity, it is only one point. Therefore, there it does not make sense to talk about minus infinity and plus infinity, all right.